All right. Can someone please remind me of the statement of Gauss's law? What does it say?
Integral E.
Catch that? What did you say?
Integral EDA.
Equals to what?
Q enclosed over epsilon naught.
Over epsilon naught. Okay? Can I have your attention, please, everyone? Okay. Q enclosed over epsilon naught is E dot dA, and this is the flux, right? This is the flux to a closed surface. Has to be a closed surface. Okay. And we're going to apply this today to, we'll start with a spherical shell, and then a solid sphere, and then we'll talk about conductors in electrostatic equilibrium, and then possibly one more example. Then that's the end of the chapter. Okay. So, spherical shell. Here's a spherical shell. Of radius A. For a change, the radius of the shell is going to be A, not R. Okay. And charge Q. So here's the shell. It would look like this. This is the radius of the shell, it's A. And the charge on it, it's Q. And again, I'm going to just assume Q is positive. If it's negative, just put a minus sign in front of the result at the very end. So here is the charge. Okay. It's a shell. It means there is only this piece to it. In the middle, it's empty, and then in the outside, it's the outside. It's empty. All right, nothing here. And nothing there. Only there's the charge right there. Okay. And the question, what do you think it would be? Find the flux field. Where?
Inside and outside.
Inside and outside. Yeah, that's it. So find the electric field inside the shell and find the electric field outside of the shell. So find for the following. Case 1, R greater than A. Case 2, R is less than A. Okay. All right, let's do case 1 first. Let's do case 1 first. Yes. R is the distance from the center to somewhere, to the outside. Yeah, the radius, yeah. So, okay. So let me, and it would be clear in one moment. So here is the shell again. I'm going to redraw it. Redraw the shell. This is A. All right. This is the actual physical object. Okay. That's the physical object. Now I need to choose it. I want to find the electric field for R greater than A, meaning R is measured from the center of the shell all the way to somewhere. Okay? And what's the electric field outside of the shell? R greater than A means R extends to outside of the shell. What kind of symmetry do we have? Spherical symmetry. Okay, spherical symmetry. So my Gaussian surface is going to be a sphere. And the Gaussian surface, when you apply Gauss's law, you want basically two things. The electric field to be parallel or perpendicular to the area and be constant over that surface. These are the two things you want. So here's the Gaussian surface. My Gaussian surface is in red, and this is R. The Gaussian surface is a mathematical surface. It doesn't have charge on it or anything. It's just a mathematical surface, not an actual physical surface. Okay? So we're going to ask the following questions. First, here are the questions. To figure that you actually have a good Gaussian surface. Is the electric field at this point going to have a larger magnitude, equal magnitude, or less magnitude than this one? It will be the same. Since you're the same distance away, it has to be the same, right? You wouldn't know if I take the shell and rotate it. Would you know that the shell has been rotated? If it's completely symmetric, yeah, you wouldn't know. So the electric field magnitude is going to be the same everywhere on the sphere. So that's already good. And then the next good thing is this. In what direction is the field, let's say, at this point? Radially outwards. You will not say it's somehow this way or this way. It will be radially outwards. Okay? Just by the symmetry again. Okay? It will be radially outwards. And radially outwards. Radially outwards. The electric field is going to be just radially outwards in all of these. How about the area vector? Also radially outwards, right? We said the area vector always perpendicular and away from the surface, the closed surface. So the area vector also points this way. And of course on this side. We're going to apply Gauss's law. We're ready for this case. So E dot dA is equal to Q that's enclosed over epsilon naught. E dot dA, Q enclosed over epsilon. Let's start with the right-hand side. Let's start with the right-hand side. Look at the red surface, my Gaussian surface. How much charge does it enclose?
Q. All of it.
Q. All of it, which is Q. Good. It encloses the whole Q. So Q enclosed is simply Q over epsilon. So that's the right side. Let's look at the left side. E dot dA. Two vectors are parallel. What's their dot product? The angle is 0, so cosine of 0 is 1. So EDA becomes EDA, and then, yeah. So it would just be the product of their magnitudes. EDA. Good. Close integral. We could skip ahead and just write EA, but let's do it in a few steps, at least for this first. We said, as long as the radius is fixed, the electric field's magnitude is constant, so we're going to pull it out. So it comes out, so we have this, E, dA. Okay. What's the integral of dA? A. And what's the area? What's this? A is the surface area, right? And what's the surface area of a sphere of radius R?
4 pi r squared.
She said 4 pi r squared?
Pi r squared.
And Q
What's a sphere?
over epsilon. So the surface area is like you add all those little dAs. You know, have you seen a soccer ball? Because these little patches. So you're adding all those little patches, and that makes up the surface area. When you add them up, you get 4 pi r squared. So E then would become Q over 4 pi epsilon naught, and then 1 over r squared. That's the magnitude of the electric field. Looks like what?
KQ over r squared.
A point charge, right? So when you're outside of the shell, as I mentioned before, now we have proven it. When you're outside the shell, it looks like as if it's just simply a point charge sitting at the center of the shell. And we also determined the direction of the electric field before getting its magnitude. So now we can put the direction. This is outside. Right? This is for a spherical shell. Okay. Next would be inside the shell. Okay. We're going to apply Gauss's law to figure out what's the electric field inside the spherical shell. So this one, I went over the argument with you yesterday or the day before for a cylindrical shell, but let's go over it for a spherical shell. It's helpful to go over it again. number 2, for R less than A, here's the shell. This is the actual object, right? This is the actual object. Radius A. Again, what would the shape of my Gaussian surface be? Spherical. Does it extend up beyond or inside?
Inside.
Inside. And it should it be a sphere here? No.
No.
It should have the same center. Good. All right. Good. So that's where it should. All right. Here's my sphere, and my sphere is going to have radius r. Now, remember, there are pluses here. So let's choose a particular point. Let's say this point here. In what direction is the electric field going to be?
Inward.
So
Toward
you
the
might
center.
think it's
Towards the
radially
center.
inward, might
Yeah.
think it's radially outward, or maybe 0. So but it cannot be this way, right?
Yeah.
The fact is this, we can't really know yet. There are arguments for saying the electric field will be radially inward. Why? Well, look at this plus charge here. It's closer to this point, so it will produce an electric field here. But then the plus charge that's on the opposite will produce an electric field that's a little smaller. So it might actually be radially inward, but it would not be the case because let's come back to this point. Okay, remind me, when I finish the problem, I'll come back to this point, why it's not going to be the case. So the main part is this. The electric field is going to either be radially inward or radially outward. Those are the only 2 options, okay? And then we will apply Gauss's law and let it determine what the field is going to be, okay? Yeah, it is going to be 0. So here it is. E dot dA is going to be equal to Q enclosed over epsilon naught. So what's the charge enclosed?
0.
Yeah, your red surface encloses this empty space. Nothing is in it. So 0. And if you remember, it's not enough that this is 0 to conclude that the electric field is immediately 0, right? We gave a counterexample when that's not the case. So it's not enough to just say, oh, therefore the electric field is 0 since the right-hand side is 0. Not enough. We need to now determine this. E dot dA. If the electric field is radially outward, what would E dot dA be? EDA. What if it's radially inward? Negative EDA.
Negative.
So it could be plus, it could be minus. I'm going to allow for both. We're going to say plus or minus EDA. Okay? Again, it would be 0. That won't be valid. Electric field would be constant, right?
Mm-hmm.
So we pull it out. So we get plus or minus EDA, and the integral of EDA is 4 pi r squared, right? We did that earlier. So 4 pi r squared equals to 0. Now, the 4 and the pi are not zeros. The r is not 0. It must be the electric field that would be 0. So the electric field has to be 0. If the right side is 0, so that this product has to be 0, it means the magnitude of the electric field therefore is 0. So plus minus is still 0. So E is equal to 0. Okay? Yeah.
Why is the charge 0 again?
Oh, where is my Gaussian surface?
Inside?
Yeah. How much charge is inside?
There's no charge inside?
There is charge. This one is a shell, right?
Yeah.
So the charge is all here.
Oh, it's not inside.
Yeah. So it's
On the-
empty. So I'm gonna come back. Yeah.
So basically, since it's a circle inside of a circle with the same center, all the force that applies to that sphere is equal from all walls.
The electric field will just be 0 inside here. So I promised I'd come back to this, right? I said this charge. So like, the math tells us it's 0, but can we kind of geometrically explain why it is? So think about this charge here and this charge here. They produce opposite fields, right? It seems like this one is going to win. But let's take this arc length here. And this arc length here. Going through here. So this arc length will include this many charges. But this arc length will include bigger, more charges. Yeah, they are farther, but get more of them. Yes. And so cancels. Yeah. That's a good question. Yeah, that's a good question. So let me. I promise I will answer. So let me plot the electric field as a function of the distance from the center. Here's R. Yeah. Here's the electric field, right? Here's A. What's the electric field from 0 all the way to the surface, not including A? 0. So the electric field is simply 0. I will leave a hole there. Okay. The function is a hole. How about in here? So there is nothing. And then what's the electric field right outside? It's
Constant times 1
this one, right? Yeah, it's Q over 4 pi epsilon naught R squared. So when you approach A from the right, you will get A squared there, right? So you get this. Q over 4 pi epsilon naught A squared. So it looks like this, and then it drops, right? It's 1 over R squared. It drops. So, Jasmine, right? Yes. The question is, well, what's the electric field at that point, at the surface? The answer is it's actually half of this. And you can go through the derivation. It turns out to be Q over 8 pi epsilon naught. But I will not go over it. The idea will be this. You can do it by integration. Direct integration is to make a little hole here. And then ask, what's the electric field here due to everything else? And then add that hole. And then you can make the hole as small as you want, and you will find that it's half. Okay. But we'll not go over that. I'll come back.
On the E-axis, what does that say in red?
This one in
Yeah.
red. Yeah. Q over 4 pi epsilon naught A squared. Basically, this one replaced with an A.
Okay.
Yeah. And yes. Yes.
Oh, that was my question.
Oh, okay. Okay. So don't worry about the surface. Ignore the surface. So outside, inside. Now we're going to go to a solid sphere. Yes.
Why is a hole not a solid particle?
Well, we found the electric field less than A, and we found it for greater than A. But what's the electric field at A? It's not a continuous function, right? I mean, it's 0 and then it jumps to some value.
Oh, yeah.
So it's discontinuous. Okay, we're going to go to a solid sphere, right? Solid sphere. Solid sphere. Of radius A and charge
Jadi R is equals to A, malah
so here is a solid
over
sphere.
A.
The radius is A, okay? But now the charge is not just on the surface, it's everywhere. So the distributed uniformly throughout the volume. So there is charge throughout the volume. Clear? So let me ask you, what's the charge density? The charge over volume. Charge per unit of volume. It's the charge over volume. So Q over what?
Q over epsilon. Volume.
4/3 by A. Right? That's the volume of a sphere. So that's the charge density. Okay. And you probably can guess the question. What do you think the question is going to be? Inside and outside. Find the electric field inside and outside. We're going to find it outside, and then we're going to find it inside. Somehow it's always easier on the outside than the inside. You have to always do a little more work the inside. So let's do the outside. So outside means R is greater than A. So here it is. Choose a Gaussian surface, right? The sphere. And it should be with the same center as this one. And we guess that the electric field is going to be radially out. So here is my Gaussian surface. My electric field is radially outward, right? Here is the electric field. And it's also the same as the area, right? We went through this exercise. So we get E dot EA Q enclosed over epsilon naught. Okay, how much charge are we enclosing? All of it, yeah, which is Q. So Q over epsilon naught. E dot dA. So this one we did before, so I'm going to not do every single step. So E dot dA becomes
EDA.
EDA. E is constant, you take it outside. So you just have the integral of dA, which is A. So you just have EA. And what is A? 4 pi
Squared.
A squared or R squared? Is this the area of the red surface or the? Yeah, it's the red. It's the Gaussian surface. Yeah. So it's E times 4 pi R squared. So the electric field is going to be Q over 4 pi epsilon naught 1 over R squared. And since it's a vector, it's R hat, R hat. So what does the electric field again look like when you're outside?
Point charge.
Just like a point charge. So whenever you have these spherical symmetric, whether it's a shell or a ball, like a solid sphere, it's going to behave like a point charge when you exit, when you're outside of it. Okay. We're going to now do inside the shell, inside the sphere. Inside. So inside. So R is less than A. The ball. Plenty of plus charges distributed. By the way, I always like to use plus charges, but if it's a negative charge, if it's actually a negative charge, what do? You just put a minus sign. That's it. So I always like plus because it's radially outward. So here is our charge sphere. So our since I want to be inside, my Gaussian surface will be inside. So here's my Gaussian surface. We have radius R. Radius R. Okay. Let's go step by step. E dot dA. Is equal to Q enclosed over epsilon naught. Now, am I enclosing the whole charge or part of it?
Part.
Part of it. What's that part?
Volume.
It's the volume times what? I'm sorry, it's the charge density times what?
Volume.
Times the volume, yes. Times the volume. V is volume, okay? Over epsilon naught. And yeah, we can do one more step. Or actually, let me go to the yeah, let's actually get it all the way. We said the charge density is the total charge over the volume of the whole sphere, right? So it was Q over 4 over 3 pi A cubed, right? 4 over 3 pi A cubed, the epsilon out here. And then what's the volume here? What's the volume of this red sphere?
Pi over 3
Pi
A squared. A cubed.
little r cubed.
Oh yeah.
Right? So the 4/3 pi cancels. Fine. We will simplify this in a moment. But let's take a look on the left side. The left side. So, in what direction is the field? Radially outward or radially inward? Yes, Leah. Inward. Why would you say inward?
Because the charge is
That's a good point. Why would you, like, if you change, like, tell me.
I was originally thinking it would be inward because the charges are on the outside, but that's for like hollow shell.
I think it'll be outward because from the other one, everything outside cancels, so that it's only going to be inside.
Good. It's actually going to be radially out. Think about the ones inside will produce a field radially outward. The ones on the outside here, they contribute nothing. Look at the shell. What was the field inside the shell? Zero. So think of these as a shell on top of another shell on top of another shell. Every shell, as long as it's outside, as long as you're inside that shell, the field from that shell is zero. So the field from this one here contributes nothing to the field here. So it contributes zero field here. So the only field, thing that contributes to the field at the surface is actually whatever the charge is included here, which will be radially out. Yes.
But if you have two charts, the one inside negative and the one outside positive.
Here?
Yeah, like the.
As long as they are uniformly distributed, they'll be contributing nothing when you're inside. So yeah, the field will actually be radially outward. That's part of why I did the shell first, because we needed to justify this.
Professor, if the inside of the electric field inside is zero, so what we have is Q on the outside, right? Wouldn't it be radially outward, just meaning like it's hard in? You know what I mean?
Can you
So
say it
if you
again?
have a Q here, right?
A Q
wouldn't-
here?
Yeah. Wouldn't it be like more, like wouldn't it be inside, going inside?
This charge, no, they are positive charges, so it will be radially outward.
Wouldn't it go away from the positive charge?
Yeah, so
So if we have a positive on the outside, so it will go inside, right?
oh, so what I'm saying is these ones, the ones outside, their field that's radially inward ends up canceling itself.
So
because
the
of this.
outside cancel each other?
So go back to this one, right? What did we say the field inside was? Zero. Why? Even though, right, this is positive, it's given a field in. Everybody's given a field in, but it ends up canceling. All of this is outside of this, so they contribute nothing. The only contributor will be the charge inside here. That's what we're trying to do. That one will be radially outward. Yes.
Dari sini tadi dari bawah. Jadi jika dia itu apa kalau aku simpul itu buat ke dalam.
That where
square is a hollow sphere inside of it. And then as for the electric field, we did it acts that we're outside of it, so it
Yeah.
treats like a flip chart.
Yeah, let me ask you this way. So, let me redraw it. Let me give you this example. Let's say I have pluses here. It's no longer a shell. I'm trying to draw pluses everywhere. It's not a shell anymore. It's a thick shell, I guess. What would be the field here if this is empty? Yeah, zero. Okay? Oh, except donut would be, yeah. So it's a sphere. It's an actual, this is a sphere, but the middle carved out. So now, if you insert plus charges here, they will contribute the field to the outside. So the answer is the field is going to be radially out. So the left side, E and dA are parallel to each other, so you end up with just EA, so E times 4 pi r squared. So E times 4 pi times r squared. We need to simplify this a little bit, so we get E and then 4 pi r squared is equal to Q over epsilon naught and then R cubed, right? Is that true? Q? Oh, there's an A cubed. Okay. This R squared cancels this. So we get E will equal to Q over 4 pi epsilon naught and then R over A cubed. And let's put the vector back. That's the field inside the sphere. I remember someone asked, how does it grows linearly with R. So let's plot that. Here's R. Here is the field. Here is A. What's the field at R equal to 0? 0. Yeah. R is 0. Yeah. And it grows linearly, right? So it grows linearly like this. What value does it have here? When R is equal to A, when R is equal to A, what do we get? You get A, so you get this, right? You get the Q over 4 pi epsilon naught A squared, right? Let's look outside. On the outside, this is the field. What's the field at R equal to A at A? Yeah, so it's the same, right? Yeah, so it will be the same as this. So that one, you don't have a jump or discontinuity. So it's going to just be like this, because it's 1 over R. So it grows until you get to the surface of the sphere, and then it starts to go at the surface. Yeah, that one was 0, and then it jumped to something. Yeah. This one is continuous. There you have charge. Yes.
How does that grow linearly?
Oh, it's proportional to R. Right. The Q, 4 pi, A, they're all constants, except for R. Good. That's fine. We're going to discuss conductors, insulators. That's the next part. So, and then if there is time, we will do one or two more examples of Gauss. Yeah.
So for the sphere, that point A, is there a, it is at that peak exactly, and it's
Yeah.
right on the surface?
Yeah.
Okay.
Yes. That was for the shell. You see, the shell was 0, and then it was this. And then you asked at exactly A, there was a jump. Whereas this one, it was, they met, both of these curves. This one when you extend it to the left, to A, and this one when you go to A, both met. They're the same. Okay, let's talk about conductors and insulators. The difference is as follows. Conductors, the charges, conductors have charges. Here's an insulator, wood. Here's a conductor, aluminum, or steel, or brass, or copper, or silver. These are conductors. So insulators and conductors, they both have charges. They both have positive, they have atoms, so they have plus and minus charges. However, for insulators, the charges are not free to move. At least they're not easily movable. They're stuck to the atom. You can't move around. For conductors, the charges actually could move throughout the conductor easily. Okay? And we're going to talk about a perfect conductor versus a perfect insulator. So perfect insulator, the charges can't move at all. A perfect conductor, the charges can easily move. Okay? So let's go over those. And then we want to discuss their properties. So I have here conductors in electrostatic equilibrium. So, please pay attention because one property leads to the next one, to the next one, to the next one. So they build on each other. Okay? So I need your attention throughout. So let's consider a piece of conductor, and we're going to apply an electric field to it. So let's say the electric field goes this way, from this way. So imagine that wall is charged what? The electric, yeah, positive, and this one would be negative, right? Yeah. And so the electric field is this one. So imagine I have a conductor. I will draw my conductor rectangular because it's just easier to draw. And we have an electric field, this one, right? This is our electric field. We call it E naught. Right? That's the electric field supply from the outside.